Welcome to YouTube channel scientific_math. In this lecture, we will write a MATLAB code for the Newton-Raphson method with the function plot and the error plot like that. This is the function plot and with the numerical solution that we have. Okay, and this one is the error plot as the number of iteration is increasing and the error in the solution is decreasing and becomes 0 after 15 or 16 iterations. So in this lecture, we will write a MATLAB code for the Newton's method. In previous lectures, we have already discussed the Newton's method derivation example, and when the Newton's method converging and diverging, I will provide the link in video description. You can watch all those lectures. So let's start to write a MATLAB code. Okay. So first we write the initial command clc clear all, close all, and here we use format short. Okay. So here we have four sections in which we write the MATLAB code. First we write the given data. For example, this one is we have the example function and the initial solution. This one is the initial solution x naught that is equal to 1, and this is the tolerance that is allowed in our solution. And here we have number of iteration. These are the 50 number of iteration. We want a 50 number of iteration. So this one is the example function. Okay. So next we have this one is the uh, initial solution. Initial solution. Okay. So next we have a tolerance that is in our solution, and next number of iteration. These are the number of iterations. Okay. So uh, in next section we will write a MATLAB. We will write a program code for the Newton's method. And first we write the Newton's method. We know that Newton's method, that is xns, that is numerical solution. Okay, is equal to, this one is the Newton's formula, x naught minus, here I will small x naught minus, okay, brackets f of x naught divided by the derivative of the function, that is, this one is the function at x naught. Okay, so here the derivative I have used df. This represents the derivative of the function at x naught. I have already saved this derivative as a function, and here you can see that function df is equal to derivative of the function at of the function f at x naught. And this one is the this one how we can calculate the first derivative of a function numerically by using the central difference. Okay, I will provide the link in video description. You can watch the video about how we calculate the derivative of function. Okay, so here I have called this function, that is derivative of the function at x naught. So this one is the Newton's formula, and yes, we know that we want a repeated iteration. Okay, so for repeated iteration we will use for loop. Okay, for I is equal to 1 to n. We want number of 50. We want 50 iterations from 1 to n, and here n is equal to 50. So this will repeat for 50 times. So then we end this with this loop, for loop with this end. And next, yes, we want also check the error in our solution. So error in x is equal to, okay, absolute of numerical solution s minus x naught, that is our initial solution. Yes, and okay, so here I will use round, round, to round off this up to 4 decimal, comma 4. Okay, so this will give us the answer in 4 decimal, and here I will put column. Next I want to check the tolerance, means that this one is we check the tolerance in our solution. So here I will use if loop. If the tolerance in the solution is equal to the required tolerance that is allowed in our solution, then this will break the for loop that we have used. So if the if error in x that is less than tolerance, okay, so when the error in the solution is less than the given tolerance, then this for loop will break, okay, and end, okay. So and then we will update the initial solution with the numerical solution. So okay, this will update our numerical solution, that is x naught. And so this one is the program code, and this is the Newton's method formula. And then we will check the error in our solution, and when the error is less than the tolerance and that is allowed in our solution, then this will break the for loop, and then we will get our required result. Okay, so this one is the program code, and we also want to show the solution in a table. So that for this one we will write over here f print f. Okay, so we number of iterations I, okay, solution, this one x naught, this one is the solution, and error, okay, that is the error we want table, all these stuffs in our table. And okay, here we write percentage 3i, okay, next with space 11 dot up to 4 decimal. Yes, there will be also percentage comma this one for solution, and next we will also write 11 dot up to 4 decimal, okay, this one for the error. And here we use backslash n for new line. So here we will see the result will be in the some error that is capital X naught. So where capital small x naught. Let's run this again, and we can see, okay, so this one is the solution in table, okay. So next we have to remove this one, there will be a space, okay. So let's, okay, so here again we want to display over here this command to display number of iterations and number of iterations with solution and also error. Okay, so here we what the error is, okay, here this ti, yes, so that's fine. Number of iteration, this one is the solution, this one is the error, okay. So we, and this one is okay, so fine, this one, okay. So okay, let's run this again, that's fine. It will be less space, remove space, okay. So here this is the code for program code, and this one Newton method. Now we want to plot the graph of the function. So to plot the graph of the function, first we take a vector x with linearly spaced BCD, okay, from -5 to 5 interval, semicolon, yes, and y is equal to f of x. This, okay. So here I will use subplot command. First I will use over here, that is figure with color white, okay. Next, subplot 2, 1, 1. Okay, which one is the to plot? That is x and capital Y and with line width of the line is 0 2. Okay, so now we is over here in line 11. Pick the color here over here. Error over here. Here. Okay, that's okay. Now we can see. Okay, so we have this one is the graph of function, and next we will also plot this. So to plot this, yes, and we also x label with x label x capital X and y label is the function that is this. So we put over here. Okay, so here I will use semicolon. Okay, next we want also plot axis dot GCA. This is the current axis, and the axis dot x axis location to set the location of the axis, that is equal to start from the origin. Okay, origin, yes, and then x axis dot y axis location. This will also from the start from origin. Okay, and we also want to off the box. This one off box off. Yes. Now we can check this over here. Some error is over there. That GCA axis is equal to GCA. Here we have axis is equal to GCA. Okay, so let's run this again. Okay, now we can see that here we have the y axis and x axis. Here we have y label and here we have x label. Okay, and there is no box around the graph. Okay, next we want to plot the graph of the error and or the plot or error graph. So to plot this one, first we write over here error. Okay, over here error, that is okay, is equal to yes, and then after this one e double r, or this will create a vector or column matrix of error values and semicolon error x. Okay, here we can see that. Let's run this, and we have this one column matrix of error or the error graph. Okay, so this one is error. Now we want to plot this error, and we put over there semicolon, and here we plot subplot 2, 1, 2. Okay, and plot the error. Yes, from 1 to I number of iteration. Okay, and then the error is this one two number of iteration value. Okay, comma with a red line. Yes, and the width of the line is that is line width WIDTH is 0 2. Okay, and we also label X label that is number of iterations, number of iterations, number of iterations with Y label. The, what is Y label? Error. Okay, Y label is error in solution. Okay, so next we also want to plot axis, that is axis is equal to GCA. This is the current axis, and next we have axis dot x axis. I will copy this from over here, okay, and paste this one over. Okay, so then I will use draw now. Let's run this code. Some error. What is the error? That is in line 36. Plot from 1 to I error this one line width, that is 2. What is the error over here? Error from 1 to I. Yes, this one is okay. Yes, this one is okay. And line width, there is some error, that is plot. Okay, so remove this end to over here. Okay, so now let's run this one. Okay, as we can see that as the number of iteration is increasing, the error in the solution is decreasing. Okay, and we will also see this one, the plot. Again we run this one. Okay, put semicolon 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 over here, and semicolon over here, semicolon 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 over here, semicolon. Okay, and the error in this solution is also okay. So it's okay now, fine now, and this one is okay. Okay, so this one is the solution of the non-linear equation, and after 7 iteration we can see that the error in the solution is 0 0. Okay, so now we again put some over right over here. If when the number of iteration is equal to n, and f print f solution is not obtained in percentage I iteration comma, that is number of iteration. Okay, so when I is equal to number of iteration, it's mean we have not obtained our required result in 50 iterations, so we will change the number of iterations, and here xns, that is the numerical solution, okay, is equal to, this will print no answer in 50 iteration, no answer. Okay, so this will end with 1. Okay, so now run this again, and okay, so we also want to plot over here the numerical solution. So to plot numerical solution in graph, we will write over here that is the xns numerical solution. Okay, xns numerical solution, and the value of the function at this one, xns. Okay, comma, and with blue box the circle red circle, and again put it. There is some error. xns numerical solution. What is the error over here? Numerical solution xns over. Okay, so let's run this again. Okay, as we can see that the solution is converging toward the numerical solution. Okay, so this one is the numerical solution, and here we have the graph of the error. As the number of iteration is increasing, the error in the solution is decreasing. We can also see with the help of table, and here we have a table. Okay, so we also want to give the title to the error graph, that is the error decay. So we will write over here that is the title. What is the title we want? Error decay. So let's run this again, and here we have a error decay. Okay, so this one is the graph of the error. As the number of iteration is increasing, the decay in the error is, we can see that after these iterations the error is completely zero. This one is the table. Okay, so thank you so much for watching my video. Please subscribe my channel scientific_math. We will also write a MATLAB code for the secant method with same procedure, graph of the function, and the graph of the error in the solution.